Hello, my name is Andrew Struthers. I am an electronics engineering technology and applied mathematics major here at Central Washington University, and I would like to thank you for coming to my presentation about Formula One telemetry analysis. So, to give a brief overview of what I will be talking about in this presentation, I will be running over what exactly Formula One telemetry analysis actually means. Then I will be talking about the workflow of this project, then some data formats and some specifics about each of these formats, and then I will be discussing some results and then future work that I can do as a consequence of this project. So to begin, what exactly is Formula One telemetry analysis? So throughout this project, I will be decoding Formula One telemetry data in the form of encoded data packets sent by the simulator Formula One 2021 by Codemasters. So telemetry gathered by the simulator includes players' car speed, steering, throttle, tire temperatures, lap times, and so much more. This project will be using a combination of C and Python to receive, decode, and display this data. Uh, Data will be sent out from the simulator encoded in User Datagram Protocol or UDP packets and then received by a Microchip PIC24 16-bit microprocessor running C code. Then selected data will be sent out via controller area network or CAN communication protocol to a different microprocessor running a Python script that will then just gather and display the analyzed data on some updating graphs. So this project serves as a proof of concept regarding data analysis and transfer on microprocessors using CAN communication. So the purpose of this project is to prototype and simulate the real-world data acquisition and analysis performed on actual Formula One cars. So while there are many more factors and pieces of information gathered in real life, taking the simulator provided data and extrapolating meaningful results will prove the concept of data analysis using a microprocessor on a Formula One car. So throughout this project, I will be using a force feedback steering wheel and pedal controller as my input device to the simulator, which will just provide a much more realistic driving experience compared to a standard Xbox or PlayStation controller. So the workflow for this project is as follows. The controller will send input to the simulator. The simulator will then simulate the Formula One car throughout the race, and as it is doing so, it will send out packets including race events, telemetry data, weather, lap data information as packets to the PIC24 microprocessor. Once the microprocessor receives these packets, it will decode and then do some data analysis on these packets of information, and then it will build a custom data structure that I created containing all of the appropriate analyzed information. Once this data structure is created, the microprocessor will then send out the data structure via CAN communication protocol to the other processor, which will then only display the information in a graph. So in figure 1, we can kind of see a visual aid for the workflow of this project. It gets pretty confusing because there's so many different places the data gets sent and analyzed. So this is kind of just is a nice visual aid to help understand the workflow of this project a little bit better. So going into some data formats used in this project, I used User Diagram Protocol and Controller Area Network through or in different stages of this project. But first of all, looking at the data that gets sent over these transmission protocols, it actually looks pretty unruly and nonsensical. So a lot of or all of the data protocols that I used have to encode the information in a binary string that ends up looking something like this long mess of slashes and X's and zeros and some random characters that don't really mean anything to a human. But once this data is received and decoded, it can actually build a really nice structure that is really nice to work with inside of code. So this long string of binary data is actually the header of every packet sent by the simulator. So to get into a little bit more about UDP, so UDP is a wireless connectionless model that implements the minimum amount of protocol mechanics relative to the rest of the internet protocol suite. So UDP is commonly used on real-time systems or other time-sensitive applications because unlike in other systems that the host sends information to the client then sends a confirmation back to the host, and then the host doesn't continue working until it gets the confirmation from the client. In sort of like a digital handshake, UDP doesn't follow that same method, and instead it just shoots data out into the world and doesn't really care where it ends up. So UDP is a lot nicer for really time-sensitive applications, because if the client in a lot of the digital handshake protocols is slow to respond, then that holds up the host, and then that messes up all of the data, and a lot of issues can arise with that sort of method. The second protocol that it used was Controller Area Network, or CAN protocol. So CAN protocol is a really standard network implementation mainly used on vehicles to transmit data between microprocessors rapidly. So CAN unfortunately has a maximum data transfer amount of 8 bytes per frame. So it's really only practical for sending a small amount of data that needs to be transmitted really rapidly. The custom packet that I'm using in this project is only 36 bytes, so it could be sent in around 5 CAN frames. And to put this into perspective, the simulator sends out UDP packets at around 2,000 bytes per packet 20 times a second, which is kilobytes of information a second and is far too much information to actually be transmitted over CAN reasonably. But gathering a small subsection of relevant data for this project and sending it over CAN is entirely doable. So now to talk about some results of this project. The simulator sends out data throughout the entire race, which could be up to 50 laps or so, which when graphed throughout the entire race ends up looking pretty useless and hard to work with, because 50 laps of data is just a lot of data. So instead, in figure 2, 3, and 4, I have broken down the data received by the simulator on a lap by lap basis, and then I've chosen to show the lap 5 data of the race that I used. So in figure 2, we can see the lap times and the sector times. So each lap is comprised of 3 sectors, represented by the red vertical bars, the blue vertical bars, and then the purple and the yellow vertical bars. So the red vertical solid bar is my best sector 1 time of the race so far. The blue vertical solid bar is my best sector 2 time so far, and then the purple vertical bar is my best overall lap time. The dashed lines are my the current sector 1, 2, and 3 times. So as we can see on this particular lap, I was actually slower in sector 1 than my personal best this race, and likewise in sector 2 and in sector 3. In figure 3, I have graphed the speed of the car throughout the lap 5. So the blue line represents the speed throughout the entire lap. The green horizontal line represents the average speed of the car throughout that entire lap, and then the red line represents my top speed of the race so far. So around 20,000 and around 80,000 milliseconds since the start of the lap, we can see that it looked like there was probably a pretty long straight, because my top speed kind of plateaued and approached my theoretical top speed of the race. Figure 4 doesn't really provide a lot of insight in and of itself, but it is a graph of the inputs to the car throughout the lap, where the green line represents the gas and the red line represents the brake. So as we can see, like I said in figure 3, around 20,000 and around 80,000, I'm full on the gas, no brake, which is kind of indicative of a long straight, and that kind of matches with the speed found in figure 3. So while figure 4 doesn't really provide insight in and of itself, it is kind of cool to compare it to the speed and see how the inputs impact the car over time. I also tried to attempt to graph steering between negative 100 on the y-axis as full left and positive 100 on the y-axis as full right, but since there are so many minute and precise steering changes throughout the lap, this graph was really messy and even harder to read than figure 4 currently is, so it didn't really help in the data analysis, so I chose not to show it in this project. So some future work that I could do with this project is I could take the tire temperature, direction of the circuit, and acceleration of the car, and attempts to mathematically model tire wear throughout the race, and see if I could come up with some sort of prediction for my lap time on the current lap as a function of my tire wear. So this would be an interesting extension of data analytics and mathematical modeling. And so the simulator also provides kilobytes of more information than what I was using for this project. So working with more data to create more charts just kind of seems like a natural progression. And finally, the simulator provides information on every other car in the race, not just mine. So I could extend this project to analyze my cornering speeds with the speed of every other car to see if I'm relatively faster or slower on a corner by corner basis throughout the lap. So in conclusion, I talked about what exactly Formula One telemetry analysis is. I talked about the workflow of my project. I dove deeper into some specifics of the data formats used. And then I discussed some results found and some future work that I could do with this project. So thank you for coming. I really appreciate you guys listening to the project. And have a good rest of your day.